So in the ninth lecture, we are going to look at some of the implications of the Bardeen-Cooper-Schrieffer theory. So before we get into the lecture, I think I want to give a little bit of a health warning. So the maths behind BCS theory is pretty advanced. Okay, it's way beyond what's assumed in this course, and indeed it's actually beyond what would be in, say, a physics undergraduate course. Of course, physicists, particularly people specialising in theoretical physics, do quite a lot more math than would be found in a materials course. But even there, they wouldn't do enough math to properly get into the details of BCS theory. So in other words, being able to derive those equations, say, from scratch. Typically, this would be something that would be done at a graduate level work for people doing, say, a PhD in theoretical physics. And there's quite a lot of sort of advanced techniques that go in there. But I should say that I think most people that work on superconducting materials don't get into the details of BCS theory. That's really quite specialist for people that want to get into theoretical predictions on those materials. Okay. What's important is actually the outcomes of BCS. So what are the equations and the predictions that it makes? And many people who work in the field, developing new materials, developing technological applications of superconducting materials are extremely familiar with those predictions. And that's what they need in order to be able to do their research. And so that's what we're going to focus on this course. We're going to focus on the results, the outcomes of BCS theory and how they can be used to explain experiments on materials. And it will also provide you with a framework to understand superconducting devices, and there'll be a third year option course on that. Right, so with that out the way, let's understand some bits about BCS theory. So we said that one of the predictions of BCS theory is that electrons can pair up in a material, and it's those paired electrons, which we call Cooper pairs, that are responsible for the dissipationless current that flows in a material. Now, this at first sight seems quite strange because in a vacuum, the force between two electrons is always repulsive. It doesn't matter how far apart you take them, you always get a repulsive force. But it turns out that in a crystal, the lattice can mediate an attractive interaction. Okay, so let me explain pictorially what that means. So here's my simple picture. I've got a material. So I've got, this is a metal. So I've got some sort of delocalized electrons all around here, and I've got some positive ions. Okay, they're the ones that have all the mass. Okay, so my first electron zings through. Electrons go very fast, so they always zing. There we go. There's my electron going through here. Now, what about the point of view of these two ions? Well, those two ions, they notice that there's a negative electron passing by, and that means they're attracted to it. But they're ions, they're heavy, they're quite slow in responding. So, there's a negative charge there. Right, great, we should move towards it. Right, let's get going. Right, off we go, and they start moving towards. Okay, so a little time later, those two ions have moved closer towards each other. Okay, now the first electron at this point is long gone. Okay, but the response time of these two ions is quite a lot slower. So at my later time, these two ions are now closer together than they would be in equilibrium. And from the point of view of a second electron coming along, the second electron says, oh, well, I see here in space, I see these two ions that are a bit closer than normal. So I see a net positive charge. So the second electron is then attracted towards that area of polarization. Okay. And so this propagates through the material. So as the first electron goes through the material, it's always causing these little polarizations, and the second electron is following it round because it's attracted to the net positive charge that it leaves behind. Okay, so that's my cartoon picture of how in a solid, electrons can actually be attracted to each other. Okay. Now, the key thing in this is that the response time of the lattice is much slower than that of the electrons, quite simply because the electrons are very light and the ions in the lattice are 1,000 or more times heavier. Okay. So when is the polarization the greatest? Because we've got these two ions, they see the negative charge go through, they're attracted to each other, they move together. How long does it take them before they reach their sort of maximum state of polarization? Well, it's related to the vibrational frequencies in the material. Okay, the faster the material is able to vibrate, the quicker it responds. Okay, so the polarization would be if we've got a so omega d is the dBi frequency. Okay, and this is the dBi frequency which you covered with Jason in the GP4 course, I think it is, on statistical physics. So the dBi frequency is a sort of average upper bound on the frequency, the vibrational frequency of the atoms. Okay, so it's characteristic of a particular material. Okay, so at 2 pi over omega d, that's the time when the polarization is greatest. Okay, so if we assume that that's the time at which the second electron feels its greatest attraction, that will tell us the distance between that will allow us to work out the distance between the first electron and the second electron. Okay, because the separation between the electrons would just be this polarization time times the speed at which the electrons travel. So Vf is the Fermi velocity. Okay, so it's an estimate of the speed at which the electrons are traveling in the material. So that gives us an order of magnitude as to the distance between the electrons in a Cooper pair. Now, from this, we could pop some numbers in. So if we look up these things, so if we look up, let's take aluminium. Okay, now in aluminium, we can work out what the Fermi energy is, which is about 10 eV. That allows you to calculate, see Chris Patrick's course, the F. Okay, and if we do that, it will be the order of about 2 times 10 to the 6 meters per second, pretty fast. Okay, and the dBi frequency is again something you can look up, and in aluminium it's about 5 times 10 to the 13 seconds to the -1. Lattice vibrations are always the order of terahertz. Okay, so that's sort of the order of magnitude that we'd expect for a lattice vibration. Now, if we pop all those numbers into our expression for D, what do we get? We get that D is about 2,500 angstroms. That's a really interesting result because that's pretty big. I mean, in terms of lattice spacing, that's several thousand lattice spacings. Okay, so the Cooper in the electrons in a Cooper pair are actually a very long way apart from each other. Okay, that tells us something because we know that there's a Coulomb interaction between the electrons that's trying to repel them. But at that distance, 2,500 angstroms, that Coulomb interaction is effectively screened out. They're not feeling any of the Coulomb repulsion anymore at that distance, but what they're experiencing is this lattice-mediated attraction. Okay. So here's the first equation that is a prediction of BCS theory. And in BCS theory, it says that the binding energy of a Cooper pair is 2 delta, where delta at T is 0. So really, just to be clear, this 0 means T is equal to 0, is given by this expression here. And not surprisingly, it involves things we've come across. So it involves the dBi frequency, omega d. It involves the electron-phonon interaction. So that's the strength of the, it's related to sort of how much those two electrons are attracted to each other via the lattice. Okay, so that's the mechanism I was talking about on the other page. And it also involves the density of states at the Fermi energy, okay, in the normal material. So we want the material in the normal case, we're expecting it here to be a metal. Okay, so there is actually a density of states at the Fermi energy. Okay, and so BCS says that if we're able to know those things, then we can calculate what the binding energy of the Cooper pair is predicted to be. And just a couple of observations on this. The Debye frequency, it's certainly possible to equate this to a sort of KT and define a Debye temperature. Again, that's so sometimes this is a Debye temperature, and that's sometimes more useful, and you'll see that in tables rather than the Debye frequency. Okay. The other thing to realize is that the Debye frequency is related to the mass. Okay, that kind of makes sense because the heavier we make a mass, the slower the frequencies of vibration. Okay, so there's a dependence of omega d on the mass, and it actually goes as 1 over the square root of the mass in an elemental material, and that would be an interesting result to keep in mind later on. What can we see from this? Well, the thing that's interesting perhaps is that as long as GEF is by definition positive. Okay, so if V is positive, and it doesn't matter how small it is as long as it's positive, delta is positive. Okay, so however small the attractive force between these two electrons in a Cooper pair, they will always be bound. Okay, it might be a really tiny binding energy, and in fact we know it's going to be a small binding energy because superconductivity in these elemental metals happens at really low temperatures. But as long as there's some positive interaction, then some positive attraction between the electrons, then there will always be binding. Okay, and that's quite an interesting result. So what does this mean in terms of the density of states? So this picture will be particularly useful when you come to interpret superconducting devices in the third year. So what we're saying is that in a normal metal, we've got our kind of like parabolic variation of the density of states, and we fill everything up to EF. Okay, this is really at T is 0 Kelvin. Okay, but what we're saying is in the superconducting state, the electrons can then bind together, and they can lower their energy. So there's actually a gap in the density of states to delta corresponding to the binding energy of these Cooper pairs. Okay, and the density of states starts off, it sort of has a pattern that's just the normal density of states like this, but superimposed on it, we've got this sort of almost divergent like behavior, and this is where all the Cooper pairs are found. Okay, so this is the origin of the superconducting gap, and that's really what we were using to understand, say, the optical properties of superconductors. Because if we're at the light frequency, then we can quite happily make excitations. There's no difference between a normal metal and superconducting metal, because on this scale, the size of the excitations is huge. It's the order of something like this. This gap here is actually really very small. It's in the millikelvin regime. And the idea was that when we looked at microwaves, this is comparable to the microwave energy. And so if we shone light on it that was smaller than this gap, the light wouldn't be absorbed. And then once we shine microwaves of a high enough energy, then the microwaves will be absorbed because they can excite a Cooper pair to be broken into two normal electrons and be excited across this gap. Okay. So this was the equation that we had for the BCS told us was the gap. Okay, the superconducting gap. And very often we're working in the weak coupling limit. So that means that the electron-phonon interaction is quite weak. So the product of V and the density of states is less than 1. And you can show that just by looking at the form of the hyperbolic sign, that will lead you to this equation here, okay, where the gap at zero Kelvin is given by an exponential form. Okay. Now you'll see in a moment why that's a particularly useful form to write, because again, another prediction of BCS is that the superconducting transition temperature is given by this formula. Okay. And the interesting thing is that we notice that this is very similar to the equation for the gap in the weak coupling limit. And in fact, if we take the ratio of those two equations, let me just pop them down on the same page for you. But so the other one that we had was delta at 0 is approximately 2 h bar omega d, and then it was an exponential of -1 over v and the density of states at the Fermi energy. Okay, so if I take the ratio of these two equations, all the material constants cancel out and I just get a number. So this is universal. Okay, so if we're in the weak coupling limit, we should expect the superconducting gap at 0 Kelvin and the superconducting transition temperature to be simply related by a constant. Okay, and I'll in the cheat sheet, I'll get you to explore how well that is obeyed for elemental solids. Many of them do obey it really extremely well. Okay, it's one of the big successes of BCS theory. It's worth perhaps thinking about this equation for a moment and saying, what would we need for a high TC? So to make the superconducting transition temperature as high as possible, what do we need? Okay, well, we need a large Debye frequency. So the faster the lattice vibrations, the higher TC will be. We need a large electron-phonon coupling, so we need a large V. We need a large density of states at the Fermi energy, so it has to be a metal. Okay. Now, there was a very early on, actually this was work of Neil Ashcroft in Cornell, Ashcroft as in Ashcroft and Mermin, one of the standard solid state physics textbooks, who looked at this and said, well, maybe in a way the idea, how can we have the largest Debye frequency? Well, if we remember that the Debye frequency omega is proportional to 1 over the square root of m. If m is as low as possible, then we'd have the largest Debye frequency. How can we make m as low as possible? Well, hydrogen. So what about sort of solid hydrogen? Would solid hydrogen be a good superconductor? Well, it would have the highest Debye frequency, so that's great. Of course, solid hydrogen is typically not, we'd have to put hydrogen under high pressure, is not a metal, so that's not going to work. But there were interesting theoretical predictions about if you went at super high pressures, I mean, we're talking about like the interior of Jupiter type pressures, maybe hydrogen itself could become metallic. And would hydrogen then superconduct? And there's been huge numbers of papers published on this, probably really quite abstract. And does this have any implication for real material science? Possibly not. But it's an interesting kind of theoretical game to play. Very recently, this has come back round because currently the highest temperature superconductor is actually hydrogen sulfide, so H2S. Okay, and you have to put this under insane pressures to superconduct. So again, this is not really going to be a very practical superconductor. But if you put it under really crazy pressures, this material does superconduct, and it has an extremely high transition temperature. I think the order of sort of 200 Kelvin, not the sort of 1 or 2 Kelvin that we've been talking about in the elemental metals. And it's because one of the reasons is because it has a very large Debye frequency, because it's the hydrogens that are doing the vibrating. Okay. But if we look at so here's some data on a variety of different materials, and we can start to understand now. So I've given you the Debye temperature, not the frequency, but the temperature. We've got TC, and we've got the product of the electron-phonon interaction and the density of states. So if we look at something, let's see what we can understand from this. If we compare, say, zinc and cadmium. So zinc and cadmium are just below each other in the periodic table. They're very, very similar. And not surprisingly, the product of the electron-phonon coupling of the density of states is in both cases the same. It's 0.18. But what is different? Well, cadmium's a lot heavier, because it's one further down than zinc. And as a result of that, its Debye frequency is quite a lot lower. And in a simple ratio way, its transition temperature is lower than that of zinc. So that's just coming about because of the change in mass going from zinc to cadmium. Okay. Two ones that kind of stand out here possibly are mercury and lead. They're both very heavy materials, and their Debye frequency is low, but they do have the highest TC, particularly lead has quite a large TC. Why is that? Well, okay, the mass isn't helping, that's definitely reducing TC, but remember that the electron-phonon coupling strength comes in through an exponential, so these have the highest electron-phonon coupling strengths. And as a result of which that factor overweighs the mass factor, and so they have the largest superconducting transition temperature. Okay. So all of these materials here can be reasonably well described by the BCS theory and the formation of Cooper pairs. And again, I'll get you to explore this data a little bit more in the cheat sheet. Okay. Another prediction of BCS is that the gap varies with temperature. Okay. Again, this was something that had been seen in optical experiments looking at microwaves, and it obeys this effectively this graph, whereby if we're at close to absolute zero, the superconducting gap is very similar to the zero temperature result that we saw earlier, okay, and it's almost flat for a while. But as we approach the superconducting transition temperature, the gap reduces until at the superconducting transition temperature, the gap actually goes to zero, it closes. Okay. This is interesting, this kind of gap, dependence of the gap. Again, it's not what we have in semiconductors where the gap is independent of temperature. And it's because superconductivity is a cooperative phenomena. So the binding energy of the Cooper pairs changes, okay? And it's largest when all the pairs are in the same state. So at 0 Kelvin, all the electrons have paired up into these Cooper pairs. And at that point, the binding energy is the greatest, okay? When you've only got a small number of Cooper pairs, the binding energy is smaller. Okay, so this is what we call a cooperative phenomena. And it's very similar actually to ferromagnetism. Ferromagnetism is a cooperative phenomena. So remember, if you looked at how the magnetism varied with temperature, actually the graph is very, very similar to this graph here. Okay, in magnetism, the more spins that align, the stronger the Weiss field, and hence that increases that encourages more spins to align. Okay, so the magnetism in that case increases the lower the temperature we go. Okay, and as we reach, say, the Curie temperature in a ferromagnet, the spontaneous magnetization goes away. Okay, so this superconducting gap is behaving very similarly to mathematically very similarly to what happens in ferromagnetism.